Welcome friends, I am Tonmoy. I welcome you all in my channel Chemistry, the Mystery of Molecules. So today we will discuss about Meerwein, Ponndorf, Verley reduction and open-air oxidation. So these two reactions are actually same type of reaction. Means if your target part is somewhat, then the another part that could be named. For example, means Meerwein, the MPV reduction. If you convert ketone into corresponding alcohol, means secondary alcohol, then that should be considered that Meerwein Ponndorf Verley reduction. And if you oxidize this alcohol into corresponding ketone, if you consider this part, then it should be named as open air oxidation. So today we will discuss mainly about the basic concept and reaction mechanism. So today's discussion will cover few points. For example, the basic concept of this reaction. The equilibrium, you see this is an equilibrium reaction. I have given the equilibrium sign. Equilibrium constant for and its other parameters like delta H, delta S, delta G, and how this factor could be overcome because of smart design. Second, nature of alkoxide. After that, mechanism, transition state, and selectivity means uniqueness, the mildness of this reaction. That's why this reaction is favored. So this and broader application which is due to its unique selectivity, which will explain in the next video. And finally, asymmetry. What is the consequence of asymmetry? As you can see, this is an asymmetry, but it is oxidized, so new asymmetric alcohol is produced. What is the asymmetry? Could it be controlled? So we will discuss this thing in this today's lecture. So let's start. So this reaction is nothing but organic redox reaction. Okay. In this context, I want to mention that previously I have uploaded 3 redox reaction lectures. For example, Clemmensen reduction, Ulrich-Richter reaction, and Mozinko reaction, where carbonyl is reduced into methylene. So that thing I have already uploaded. Please go through that. I shall provide the link in the description box. So this is also a kind of organic redox reaction, but one reagent is responsible for reduction of another reagent, and it's a completely equilibrium process. Okay. So if we want the oxidation of an alcohol, then what we need? We need a sacrificial reagent, that is oxidation of an alcohol to ketone. Then sacrificial reagent must be the ketone. Okay? But another thing, if we want to reduction of ketone, then we have to use sacrificial reagent like alcohol. Generally, I want to mention generally, please don't make it as a common sense. Generally, if you needed alcohol oxidation, acetone is used as sacrificial reagent. Alcohol is needed as sacrificial reagent. But if you need oxidation of alcohol, but if you need reduction of ketone, then we need a sacrificial alcohol. For that case, generally, this isopropanol is needed as sacrificial reagent. Okay. Now what is the criteria of a sacrificial reagent? Either it must be ketone or must be an alcohol having a alpha hydrogen. Okay. Means adjacent carbon should have an hydrogen. So this is, and here there is a hydrogen. This is 2-propanol. Okay. So this is the important thing you have to keep it in mind. But if you think about the background when this reaction was done, at that condition, what was used? That was used alkoxide, means aluminium ethoxide. So the alkoxide was generally, previously when it was used, aluminium ethoxide means OCH3. So if it is previously used aluminium reagent, means aluminium 3 isopropoxide, then why we are saying about this secondary? Because you can see this is a primary. This is a primary alkoxide. This is a secondary alcohol. Then why we are choosing this? Because it has a reason. For example, if this primary is oxidized, if you can consider the corresponding primary alcohol, So I will explain in the mechanism part, you will understand completely. Just right now keep this information in your mind. So if we, and they have done the reaction in ethanol, CH2OH. So if they have done the reaction in ethanol instead of isopropanol, what was the product obtained? Corresponding carbonyl compound of ethanol. So this is actually acetaldehyde. Okay. So this is acetaldehyde. And if we use isopropanol, this product is acetone. Fine. So now if you compare this versus this, difference is 1 ketone. And if you want to understand this completely, you need to understand one point. Role of this aluminium alkoxide. Its role is first A, acts as Lewis acid. Second, it is a hydride transfer reagent. I shall explain this thing during the mechanism. Hydride transfer agent. And the last criteria is act as base. How to understand this? Remember, during Claisen-Ester condensation, we have used that aluminium, sodium ethoxide, which is acting as a base, and alkoxide can act as a base. This is aluminium. Reactivity pattern may be changed little bit, but basic criteria is expected to be same. Fine, that it can act as a base. So another, and we have observed that aldol condensation needed alkali, means KOH, NaOH, but if we provide alkoxide, then also eventually there is a better, because alkoxide is more soluble compared to simple hydroxide. So it can act as a base, means this ethoxide can act as a base. And we know that aldehyde can undergo aldol condensation, means aldol easily. If aldol, they can perform the aldol condensation easily. What is the advantage or disadvantage? That the product can undergo aldol condensation. But if we have acetaldehyde, we know that acetaldehyde cannot participate or cannot undergo aldol condensation that much efficiently because of the bulkness, because of this 2-methyl. And in this context, I want to mention, I have uploaded a video about Burgi-Dunich trajectory. Burgi, actually you may say Burgi also, that is another type. Burgi-Dunich trajectory. So this is a guideline which explains why aldehyde is more efficient or prone towards aldol condensation, whereas ketone no, because of bulkness, everything. I have made a video, so please go through that. I shall provide the link in the description box. Fine. So we have discussed about the corresponding alkoxide. So one point you should keep it in mind. How to choose? I have written R. What is the guideline or criteria to choose alkoxide? So in this context, I suggest you that keep few factors in mind. What are the factors? First, alcohol and alkoxide should be similar origin. What do I mean? Because if you think about this alcohol, actually alkoxide is produced from alcohol, so we have to select a particular alkoxide whose corresponding alcohol is reacting here, one point. So such that, because we are using aluminium OR3, AlOR3, and we are using R prime OH. So you may expect that during the reaction alkoxide exchange may occur. Means exchange, what do I mean by this statement? Alkoxide exchange means they react and produce AlOR2 OR prime plus this ROH. So right now see in B medium another alcohol is there, so they may create confusion. So for that reason, this is one. First choose both are same. R should be equal to R prime if possible. Another, if it is not possible for you, then instead of this, just choose aluminium tertiary butoxide. Why I am saying OTBU thrice? Because tertiary butanol, if you see its structure, this is a tertiary alcohol, OH. So tertiary butoxide means O minus. So if it is tertiary butoxide, then no hydrogen is here. So which it will transfer? It cannot transfer. So that reason safest chance is this isopropoxide. So tertiary butoxide. But one problem also there. When you are using this is a tertiary butyl, so steric bulk also increases. Steric bulk, steric effect becomes influential. I'm not saying that reaction will not occur, but it will influence the reaction. Okay, so I believe this point is better to choose the proper reagent for this conversion. Okay, so this is the aluminium alkoxide part. Is it possible to avoid alkoxide? Yes, possible. There are one modification by Professor Woodward. So I shall explain in the second part of this video, not here. This is a very basic concept I am discussing. In that video, in that strategy, they have used potassium alkoxide. Okay, so that's a different thing. So we have discussed about the alkoxide part. Now question comes. Okay, we have discussed basic concept. Now equilibrium. Okay, nature of aluminium alkoxide we have discussed. So let's discuss about the equilibrium. See, here one carbonyl, one alcohol, reducing one carbonyl, one alcohol. So from delta H, if we see the bond enthalpy almost equal to 0. Why I am saying almost? Because depending on the substitution, sometimes this thing should be very minute change possible. But major contribution is coming from the bond which we can control here. First point. Second, if we think about delta S, what is the point? See, 1 and 1 producing 1 and 1. So delta S is also 0. So we know that delta G equal to delta H minus T delta S. So 0, 0. So ultimately delta is 0. Another thing we know that delta G equal to minus RT lnk. So if delta G equal to 0 minus RT lnk, this equal to 0, so K equal to 1. What does it indicate? 50-50 mixture. 50-50 mixture. What do I mean? Remain 50-50. Okay. So question is, how to drive the reaction in the forward direction? Means whatever you understood during this discussion that this reaction will happen. It will convert there, but 50-50. But when we are doing a reaction, our target is to get a particular product in 100% conversion with a better yield. But we are not getting here. So the strategy, now the challenge is how to make the reaction complete. Okay. So what was the problem here? The nature of the alcohol and ketone, these are almost parent compounds are same. So if we can tune a little bit, instead of alcohol, for example, we need to reduce carbonyl. This is our target. Means MPV, Meerwein Ponndorf reduction. We are focusing on MPV reduction. This M is Meerwein Ponndorf Verley reduction. Okay. Then what we can choose? We can choose reduction alcohol we have to choose. So for that purpose, so we can choose for this MPV reduction that we have to separate. Means what is happening? Our target is now MPV reduction. This is our focus, so we have to reduce this. So one sacrificial alcohol we will use which will oxidize and prepare ketone. For that reason, we have chosen isopropyl alcohol. What is the another advantage of isopropyl alcohol? Is that it produces acetone as a byproduct. And if you see the boiling point, this is more than 80 degree, means ethanol is around 100 degree. Let's consider this its temperature, and its boiling point is around 54 degree. I am not sure about it. I am not sure about boiling point. Just I am giving a qualitative idea. So BP less. So if you heat, you can expect that this will go and it will be extracted or distilled off. It will be distilled off. If we distill off this, then equilibrium will shift according to last second principle. This is the one strategy. Now, if our target is the oxidation, means open air oxidation, then what would be the strategy? So, if we want to have open air oxidation, then we have to need a sacrificial ketone. Fine. So, I am just writing OP oxidation just to save time. There are no convention to write it in this way. Okay. So, fine. So, we need a sacrificial ketone. So, in that case, if you want to make the equilibrium right, we can do, for that purpose, we can do take para-benzoquinone. This is as a sacrificial ketone. So, let's consider SK. Okay, so this is, and what happens that alcohol is giving hydride and getting oxidized. Oxidation. So that hydride is taken by this, and ultimately what happens? It forms para-benzoquinone. Fine. So if it is para-benzoquinone, then the driving force for this forward reaction is aromaticity. And you know that aromaticity is a very important and contributing factor for the driving of a particular reaction towards a particular site. So this is the reason this hydride transfer resulted aromatic stabilization gaining. That's why this process goes forward direction. Okay, fine. So we have discussed this role of individual reagent and conditions. So now let's discuss about the mechanism and transition state. So mechanism is how this reaction is happening. So when try to remember what you have read just some time before. I always suggest you just don't look at this and focus, because majority of things I have already told during the previous discussion. What? Role of aluminium reagent. So what happens? Aluminium is acting as a Lewis acid, means somebody will coordinate to it. So what happens? This aluminium, let's consider these two OR here and here, another OR is here. So when a secondary alcohol, so R3, R4, this is hydrogen, this is OH. So what can happen? That aluminium 3 is a Lewis acid. Lewis acidic. Why? Because its outermost valence shell contains 6 electrons. So it needs another 2 electrons to get stabilized. You will say that there are many lone pairs which will contribute to stabilize. But see, this factor is like that. You are giving some amount of food to a hungry people. So what will happen? That hunger will be reduced some extent, but it will not be that person is completely satisfied or got rid of hunger. It is not that. Hunger is still there. So we need a proper or adequate amount of food such that hunger could be quenched. For that purpose, this alcohol can go and coordinate. Means, what do I mean? This alcohol can come and coordinate to this center. So what will be the thing? First it will form a tetrahedral intermediate, means aluminium, this 4 intermediate. And here this is this, for example, this is R3, R4. Fine, no problem about this. But the question is, after that aluminium will have a formal negative charge, that is also not stable. So means The thing is that you are extremely hungry and you have given food more than your need. But for example, you have given a big bread. So if you eat the complete bread, you will not feel good. If you don't eat the bread, you will not feel good. Then smartly you will say, okay, let's cut the bread half and eat, and let other half keep it. But that's not possible in case of electrons. Okay, so that's why this giving and taking will be continued. Fine, keep it in mind. I believe this is a strategy to remember about the factor. Fine. So this is OR. So right now what will happen? One OR will leave. So if one OR leaves, then what is the consequence? If one OR leaves, then it will result this aluminium OR, and this is alkoxide. Fine. See, this is nothing but alkoxide exchange. This is nothing but alkoxide exchange. So first step is alkoxide exchange. Fine. Second step, what will happen? Since this alkoxide exchange is happened, so in next step, the ketone will coordinate to the aluminium. Reason? Same reason. Same reason means, what do I mean? That this is a still 6 electron species, electron deficient, and we know that carbonyl can also perform the job as a Lewis base. Okay, so this is the carbonyl. So I am not writing R1 everything. Okay, so this is okay. Let's write, otherwise you may feel confused. I am not right. Let's avoid this OR thing every time. Just this Al. So one side is carbonyl. This is R1, R2. Another side is alkoxide with hydrogen. This is R3. This is R4. This is the minus. Fine. Now, previously I told that if you want to avoid this part. What do I mean? That here, if you take the corresponding alcohol and the alkoxide are same, then this exchange is not needed. Actually, I am not saying that exchange will not occur. Definitely occur. The process is dynamic. Mixing will occur. But then we need to think about that because both are same. So ultimately, no conclusion. So what is the important thing here? Right now, see this aluminium, everything under coordinate. Okay, under this, both are coordinated, means both are held by aluminium. Now what happens? This is electron rich, so means another lone pair is there. So this will push, this hydride will shift here and it will open to the aluminium center. So this is the reaction. So if we draw the transition state, what should be the actual loop of transition state? Transition state should look, this is aluminium. See, we will focus only those bonds which are getting broken. So this R1, R2. Fine. This is oxygen. So here another oxygen, this R4, R3. And now focus which bonds are getting broken during the process. See, or form, broken or form. This bond is broken. Actually, this lone pair, or better we should say, it will reduce that confusion. This bond, okay, this bond. So this is the hydrogen. Hydrogen. So this bond is getting broken. Here one bond is formed, means ketone for this. So this bond is getting broken, this bond is getting formed. Here also this double bond is getting broken, and actually it is a coordinate bond previously, but right now it is a actual covalent bond. Okay, fine. It's neutral. But right now it is O minus, so in this way these many bonds. So how many electrons are involved in this process? So here 2 electron from this, 2 electron from this bond, and 2 electron from this bond involved. So 6 electron involved. This is a 6-member cyclic planar transition state. So this is the structure of the transition state. Okay, so keep it in mind. This is the structure of the transition state. Fine. Okay. Now we have discussed about the mechanism for the formation of transition state. Now another thing, asymmetry. Let's discuss about the asymmetry. After that I will discuss about the mildness of this reaction. Okay, so let's discuss about the asymmetry. So from this discussion you have understood that actually, okay, don't be confused that if this hydrogen is shifted from here to here, what will be the product? So I should write it. This is O, this is R1, R2, H, R1, R2, H, this coordinated to aluminium. Similarly, this is a carbonyl, R3, R4, this is coordinated to aluminium. So if they leaves from the aluminium, means detached from the aluminium, what is the product? This is the alcohol, this is the ketone. Fine. So these are the products. Okay. So this is the completion of the catalytic cycle. Now let's focus about the asymmetry. So see, if the alcohol is asymmetric, or okay, if the alcohol is asymmetric, its asymmetry will be destroyed. I agree. Why? Because it's forming a ketone. It's a trigonal planar sp2 hybridized. Then how the asymmetry of this center will be retained? Not possible, because asymmetry means it should be attached with 4 different groups, and here it is not 4 different groups. So no problem, nothing, not possible. Fine. But what about this? Will it be asymmetric or not? Actually no. It will be racemic. Why? The question will come from here. We have this molecule. Okay, it has a both side, one bottom side, one top side, planar molecule. So hydride could be transferred from both sides. Hydride transfer. So if bottom side transfer, one enantiomer will be produced, and if off side transfer, same. And in this case, probability of hydride transfer from both sides is equally probable. Okay, so we'll get racemic, means 50-50 of each enantiomer. Okay, one thing I guess I forgot to mention, that it should not be planar. I guess if I say that's wrong, it should not be planar. It should be chair-like. What do I mean? It should be chair-like. Chair-like means, let's draw a chair. So this part, so this is hydrogen. This is transferring from R4, R3, R3, R4. Fine. And this is actually alkoxide. So this is a donation to aluminium 3. All this here. Fine. Now here this hydride is transferred. Fine. So this is oxygen, and this is R1, R2. I guess it is difficult for you to understand. Let's redraw a little better way. It will be helpful. So this is oxygen, this is oxygen, this, and this is also coordination. So what happens? That this hydride donated in this way, this bond, double bond is formed in this way, and this one bond, it will be converted into alcohol. So this. So transition state, if we discuss, we should discuss in this way. This is, and this is a chair-like transition state. Okay, so I guess this will be more. This R1 is in axial, this is in axial, this is in equatorial. So it depends, because the bulkness, I am just arbitrarily put the bulk, we don't know what is actually this R1 and R2. So depending on their bulkness, their position will be determined. Okay, fine. So this is not a, this is cyclic but not planar. Keep it in mind. If I said mistakenly. So selectivity and mildness. So the most important part of this discussion about the selectivity and mildness. You see here, during that whole reaction, what we have used, what hard reagent or harsh reagent we have used. We have used aluminium alkoxide. You can say this is a basic reagent, so which we have used for this process. Fine. But nothing difficult or harsh reagent we have used. So for that, this is a milder reaction condition. This is a milder reaction condition. And second, I told the method, for example, benzoquinone and this acetone remove benzoquinone's aromaticity, parabenzoquinone's aromaticity gaining, and acetone's low boiling point that it should be evaporated. So in this way, equilibrium could be driven. So this is one of the milder process, and this is chemoselective. Chemoselective. Okay, means functional group selective, or you can say, or functional group selective. What do I mean? Because if you have carbonyl, other than means if you have only the carbonyl group, no other that much important functional, means if you have carbonyl group and compared to that you have other functional group also, so it will react selectively to the carbon. See, because of this unique reactivity pattern. What do I mean physically? If you take an alpha beta unsaturated ketone, it's a rough example, exact example I shall provide in next video. So where I shall discuss about the application and examples, not the modification test. So if you have and you react with this secondary alcohol in, for example, aluminium, OIPR, isopropoxide thrice. So what will that? It will transfer and it will form alcohol. Selectively, no hydride transfer will be this. So this is actually a alpha beta unsaturated ketone. Unsaturated ketone. So this alpha beta unsaturated ketone you have, so it will never attack here, it will attack here. Instead of that, if you have this conjugated or multiple, it will never attack these double bonds, and this is the uniqueness. And that's why these some biomolecules which have many other functional groups which could interfere in some other reaction that could be converted oxidized in this. What is the advantage? Generally, if you see PCC mediated oxidation, pyridinium chlorochromate, swan oxidation, so in those oxidation they are relatively less functional group tolerant. Compared to this is more functional group tolerant. Okay, so this is the uniqueness of this process. So this is the end of this discussion. So what we have learned, the basic concept and mechanism, equilibrium, role of reagent, role of carbonyl, alkoxide, ketone, how to drive the equilibrium towards our desired side, what is oxidation and what is reduction. Based on our interest, this reaction should be named as oxidation or reduction. Mechanism, transition state, and stereoselectivity of this process, and finally the functional group tolerance or chemoselectivity we have discussed. In next video I shall discuss about the modification, two modification I shall discuss, and after that I shall discuss about the application and example related to this reaction. So thank you everyone for listening my video. So I suggest you please share this video among your friends so that many people will be benefited from my effort. So stay happy, stay blessed. See you in my next video.